our second meeting in this course, Mat 812, where we are going to continue to discuss on manifold. You could recall last week we treated the history, and we need silence outside. We treated history, and also in that lecture we did some review on the basic concept which will require an understanding of the subsequent areas we are going to tackle under this course. For example, we discussed what we actually call homomorphism, group homomorphism, which is a mapping from group to group, preserving the structures, of course, of the groups under the binary operations, respective binary operations of the group. And we discussed the basic terminologies of topology. What is topology? And so this we did in our previous lecture. Today we are going to continue. We even actually mention and discuss what we call manifold. And now we are going to continue with discussions on manifold, and if time permits, inshallah we shall move on to what we call homotopy, map between topological spaces. So in the manifold, remember we discussed, in the manifold we are going to be treating what we call charts and atlas. Okay. Now, supposing you have a manifold, let M be a manifold. And let me draw a typical manifold, for example. So this is my M, okay? And suppose I have a point here, maybe X, inside the manifold, okay? Now this point is going to create a neighborhood. You remember our discussions of neighborhood. Number of points around it. Let me use, can I have another color? Maybe. Okay, suppose, so that you will see what I mean. Suppose this is my X. Let me say this is my point X, and this point X is within some neighborhood, okay, of M. So let's say this is some U now, some open set. Remember my neighborhood, what we call neighborhood. By definition, what is neighborhood of X? A set of all Y, so that X minus Y is less than some R. So this is some neighborhood of radius R, okay? Sometimes you can also write it like this, neighborhood of X, okay, centered at X with radius R is this, okay? So you have this is an open set in the neighborhood, okay? Now, if you now apply some map on this point onto some two-dimensional space, okay? Supposing you have a mapping, maybe theta, okay? So this is theta of X. This is theta, the map, and it produces an image here, okay, which we call theta of X, okay? Theta of X. Now, and supposing you have maybe another point here may be y, okay, which is also define another. So if you call this theta 1, if you call this theta 2, and you also project this on two-dimensional space, this will be theta 2 of y, maybe theta 1 of x, theta 2 of y, okay? And they are going to produce every point, by definition, every point in the manifold is going to produce some open subset in Rn. In this case, R2. This is R2, two-dimensional Euclidean plane, isn't it? That's the definition of manifold. Any point you take in the manifold, it is locally what? Homeomorphic to some open set in Rn. In this case, we are taking R2. So we are now going to require that both theta 1 and theta 2 are homeomorphism. Okay, meaning that they are all invertible. Both theta 1 and theta 2 are what? Invertible, and they are also continuous maps. Now, the pair, let me call this V. Now, let me define like this. Now, the pair U theta 1 V theta 2, okay, called charts. Okay, so this is going to produce a pair U coupled with what? The map on U, that means theta 1, okay, and this is a V theta 2, yes. Now these are actually what we call charts. Okay, so this is a chart of this. The V theta 2 is a chart for the open set V, for a point in the open set V. Now, and the collection A, which is a pair of all Ui theta I, where Ui are open subsets of what? Of the manifold. And theta I are maps. This pair, this collection, and so you are going to have U1, theta 1, U2, theta 2, and so on up to maybe U and theta. This collection is called atlas. Okay, when you collect all the charts, because this is going to produce maybe U1, if I call this U1, B1, maybe you may have another one here, U2, you have another one here, V2. So you are going to have so many of these open sets in the manifold. And it's going to now generate this collection, which we now call the atlas. Now, what is the significance of this? The significance of this is, one, it helps us to visualize images of the abstract space manifold on Euclidean planes, two-dimensional, which you all are familiar with. Is it clear? For example, let me say this is maybe satellite, or what we call space. Maybe my M is the space, and I have a plug here, and I want to project the image of this plug onto my Earth surface, maybe two-dimensional, So it may appear like this on this. Maybe it could appear like this, okay? So this plug here on the moon, let me say on the space, may appear exactly like a plug on this. So I will call this, let me even use different color. Suppose I have it like this. So I say this is plug on Earth. This is my plug on space. What it means is that I can now visualize this image which is in space to make it look like or it is on two-dimensional space. And this will help us now to transmit codes, transmission, and direction, even the positioning system. You heard of GPS, where you now know where Sokoto is from the satellite. Is it clear? You now can see the coordinates, which now identify where Sokoto is within Nigeria. And you can also use the same coordinate to identify where Sokoto State University is within Sokoto State by transform. This is called transformation or transformation, okay? By these transformation maps. This is one of the uses of this. Secondly, like I said, it allows us now to study spaces on real using from abstract space, the manifold, which is some say is dimensionless, to the real line, to the Euclidean plane where we know the direction. So we can now use this to treat all these convergence of sequences, limits, and so on and so forth on the real line, which we are familiar with. So that is it about the atlas. I think if you have any questions, you can ask.